Okay, what? Anyone who can, okay, I think it's settled. So, yes. To introduce the pin architecture, I will use some example. Famous example is the Navier-Stokes equation, which is very hard problem. Navier-Stokes equation is composed of the continuity term, which is del multiplied by u equals 0. And then there is a momentum conservation, which looks like this. And if 저것도. Okay. If one wants to solve the Navier-Stokes equation using the neural network, you can use the collocation points, which is random example from the domain of the Navier-Stokes equation, and then construct a neural network architecture. Then put the each collocation point as an input, then it will output some approximated state variables so that the entire neural network architecture will approximate the state u hat, which is an approximation of the true u. And using the output, you can also calculate the loss L. If one only use the data as the input, then the loss function looks like this. And obviously, since the Navier-Stokes equation is very dynamic and very chaotic, it will fail. So to alleviate this problem, we can reformulate the Navier-Stokes equation into these type of auxiliary equations, which is Fs and Fu and F3, which can be reformulated by the continuity term and the momentum conservation equation. So if our approximated u hat is the correct one, then this term should be 0. And in addition to that, as all the PDE, partial differential equation has, there is an initial condition and boundary condition. So using this information, in order to inform this physics constraint into the neural network, we can just add up those equations into the losses alongside with the data. So the brilliant part of this is that it accepts the loss landscape is already complex, so that if you make the loss even more complex, the gradient descent method is very powerful method, so that it can eventually we are just hoping that eventually the neural network will converge to something that can be called as the global minimum.
Can you show previous loss? Yeah.
This data and the final outputs are how much different deviates from the true values.
Just the left side Navier-Stokes equation is better rather than right side too.
I It's not kind of obvious. Yes, because the left-hand side are it's actually the same because we just reformulation of the left-hand side.
리포뮬레이스를 하는 이유가 뭘까? 왼쪽 걸 핀으로 넣을 수도 있고 같은 식이니까.
It's obviously the same because the terms are just divided into, if you put the left-hand side into the loss term, then it just multiply by the vector multiplication, then eventually you get the same equation as the loss term.
처음 들어본 기술도 그냥 처음 들어본 그냥 리포뮬레이션 아니에요? 똑같은 식이거든.
예, 그 똑같은 식인데 그냥 보기 좋게 리포뮬레이션을 했다 수준. So we're just hoping that the gradient descent method is powerful enough to goes to the global minimum, even though our auxiliary losses makes the loss landscape even more complex. So as a summary, by accepting a notorious difficult loss landscape in the hope that gradient descent can navigate it, ultimately we are trading optimization stability for the interpretability of physics-bound constraint, which we wants to converge. But pinning is not a perfect method, as we all know. It has its own downside. If we have first, at first we have only the data term, which is just a single objective optimization, which already has a complex loss landscape. But if we extend this to the multiple objective optimization problem, it makes everything worse. So loss landscape gets even more complex. And so it will make the convergence almost impossible. In addition to that, since our problem became a multi-objective optimization problem, it will occur problems like this. One is the gradient imbalance. If a initial condition loss is scale of the initial condition loss is way greater than the scale of the partial differential equation loss term, then because of the gradient descent method is kind of greedy, it will reduce the initial condition more than while ignoring the loss term of the partial differential equation. So it will output functions like initial condition function rather than explaining the whole system. And the second thing is the completing gradient, which can be explained like this. So we have a 6 losses. So and we want to converge. So if we use the gradient descent, they will go downward, but in different directions. So you can view that as there is a 6-passenger in a bus, but everybody's hands is on the wheel. So if one wants to go to the right and the other wants to go to the left, it will not converge and just crash into the building, right? So that's the problem. It will oscillate through the local minimum rather than goes to the global minimum. So it can be summarized as this. And our ultimate goal is to solve the dynamical system and the chaotic equation that we cannot solve. For example, Navier-Stokes equation is one of them. This is very challenging because it is one of the millennium problem for a reason. So it is kind of reasonable that pin fails on this kind of equations. But what about the Vicious-Burgers equation, which looks like this? And it is relatively easy and well studied and well explored by humans, and one can solve it by using hand. But even in this kind of equation, pin struggles because there is a little bit of chaos, means chaosity, and there is a steepness. So everything on this slide makes the complex loss landscape even worse. And the additional problem of the pin is that it suffers from the non-causal treatment of time, because as you see the partial differential equation, which is Burger's equation, we have an initial condition looks like this, and it will evolve as time t evolves to 0 to t large t, and it will looks like this. So we want our neural network to learn the dynamic of the Burger's equation, which looks like this.
나 저희는 없앨 수 있는 거. 여기 제목이 안 나와. 검은색 나와.
지금 뭐라고 쓸 수 있나? 파워포인트로 가야 돼? 갔는데 이런. 다시 공유해볼까?
예.
Okay. So let's see, construct the neural network system using again, then we can say an input batches and the neural network architecture and the losses, which will initialize the value like this, equally very high. And then we put an input batches in order of I. One goes first and other goes again, and iteratively it goes, all of them goes into the neural network system. And suppose in the early stage of the learning, with a bit of luck, where the early stage of the learning batches, where ti is closer to t rather than 0, so it learns the later stage of the partial differential system equations system. Then, as you can see in the loss of the initial condition value, it does nothing with the later dynamics. It only reduced when the u is closer to the early stage of the initial condition of the function. So if we learn the later stage of the dynamics first, then loss term reduced like this. And at the later stage of the learning, we will have a data that ti is closer to 0, which will want to learn the initial condition values. But the neural network already learned that how to stay steady on the large initial condition loss term. So even though we put data from the ti equal the closer to 0, it will looks like this. So what we want was to neural network to learn the dynamic of the system, but in the extreme case, if it just outputs the final stage of the system. So in summary, there is a two problem by revisiting the gap sentence.
뭐랑 위에 거랑 뭐가 차이? What is the difference between the top and the bottom?
Top and bottom.
The right side.
The thought is not different; they are the same. So this is the output of the neural network. But the output of the neural network should be like this. So explain the entire dynamics of the partial differential equation. That is the whole reason why we use the neural network. But if we learn the later stage of the data first, then it will not reduce the initial condition, so that it kind of ignores the causality of the initial condition and just outputs in an extreme case, it will output the final state of the system. So that is the reason why I put.
오른쪽으로 배우냐 왼쪽으로 먼저 배우느냐 차이. 지금 오른쪽으로 먼저 배운 상황 가정이 오른쪽으로 먼저 배우고 나면 이니셜 컨디션에 대한 정보를 나중에 배우기 시작하는. 그 시점부터 배우죠.
네, 맞아요.
마지막 영상이 뭘 의도하는?
마지막 영상이 그 뉴럴 네트워크가 이런 시스템을 배워야 돼요. 이런 다이나믹을 배워야 되는데 이걸 배우지 않고 그냥 마지막 스테이트의 로스를 최소화하는 것만 집중을 해서 마지막 스테이트만 아웃풋을 내는 거예요. 네. So we suppose the extreme case. If it is really extreme, then it will result like this.
1번과 2번 early stage of learning, later stage of learning인데 이렇게 했을 때 차이가 뭐가 나온 게 있어요? 아니면
차이가 아니라 그 러닝 프로시저가 이제 쭉 있을 거 아니에요. 그러면은 얼리 스테이지에서 t가 클 때, t가 라지 t에 가까울 때라는 거는 이제 나중 스테이트의 그 다이나믹을 먼저 배우는 거예요. 먼저 배우고 이제 그 다음에 이제 초기 밸류를 그 먼저 얼리 스테이지 러닝이라는 게 그 러닝 프로시저가 이렇게 쭉 있을 때, 그러니까 배치들을 이렇게 안으로 계속 집어넣을 때 앞쪽에 위치된 먼저 들어가는 배치들이 t의 값이 크면은 그 라지 t에 가까울 때는 이제 요 오른쪽 레이더 파이널 스테이지 스테이트 값을 이제 배우겠죠. 먼저 배우겠죠. 근데 이제 사실 그러면 안 되는 게 원래는 이니셜 컨디션에서 이제 이볼루션 하는 그 커설리티를 배워야 되는데 파이널 값을 먼저 배우고 그 다음에 이제 이니셜 컨디션 값을 낮추려고 했고 그 낮은 스테이트에서 노력을 한다고 해도 이미 뉴럴 네트워크는 그리디하기 때문에 이미 이 이니셜 컨디션의 로스 값이 큰 상태에서도 데이터가 들어와도 이제 그 상태에서 스테디하게 유지를 로스 렌스 스케일에서 스테디하게 유지를 할 수 있는 방법을 배워요.
그냥 처음부터 넣으면 되는
예.
거. 나중에
네.
나중에
나중 값을 이제 또 배우는 그런 게 생기죠. 그러니까 이게 생기는 이유가 이제 the reason why this happens is that we just assumes that t value is an additional space value rather than accepting not informed that t cannot be reversed.
이게 모든 콜로케이션 타임들을 되게 인디펜던트하게 다루고 있어서
네,
생기는
맞아요.
네, 물론 그러니까 꼭 이렇게 될 거다라고
So this is the reported cases. Yes, it's not always like this, but there are numerous reports that it might happen.
Before we begin from the initial condition, the analysis should be okay.
Yes, that's correct. But the other losses will be fully learned, so the prediction of the entire system would collapse.
먼저 한 해를 먼저 줄이고 그러니까 시점에 따라서 아무거나 랜덤하게 집어넣나 하더라도 어떤 시점은 나중에 어떤 시점은 어떤 순서대로 무조건 집어넣는.
So this is the problem of the primitive approaches of the Pinto, the earlier models, like the 20, early 2020s. So yes, there are several methods that handles that kind of problem. So as you can see,
그러니까 기존의 연구에서 리포트가 되는 건 알겠는데 왜 그런지 이해를 해보자는 게 지금 이게 우리가 이해를 했다는 뜻은 앞단부터 넣으면 뭐가 문제를 그러니까 그러니까
then it will be reversed.
먼저 배운 애들을 잘 맞추고 나중에 배우는 그러면 먼저 들어온 애들은 잘 맞추겠죠. 뭐 결국엔 나중에 들어온 애들은 맞추면 안 돼. 우리가 원하는 유니폼하게 잘 맞추기. 그러니까 걸로 해서 한수공간 조금 많은 그리고 한수공간에 좀 수가 조져 있어. 얘를 먼저 그러니까 이것도 결국에 사실은 복잡한 랜드스케이프에 의해서 발생하는 거거든요. 그걸 미니멈에 얘를 먼저 줄여버리는 그 미니멈 나고 못 빠져나오고 있어. 네. 처음 걸 집어넣는데 처음 거 유사한 공간에 목표물이 빠졌어.
Can we move on? So to alleviate this kind of problem, there is numerous methods that have been developed, including the time causal, non-causal treatment of time t. But none of these methods are directly solve the problem because while we are sticking to the gradient descent method and the neural network architecture, the core problem cannot be solved if those can be viewed as patches to just temporarily alleviate the problem. So the other suggests a framework to resolve both problems via sampling basis functions, which is a method that utilize the neural network system, but not using the gradient descent-based optimization. And that will be explaining this stuff will be first part of my talk. And on the second part of the talk, I will explain the method that solve the non-causal treatment of time. So let's start from the beginning. So there is a neural network system which will approximate the true functions, which look like this. And there exists a true function. And if in a sufficiently abstract setting, we can say that this true U, is in a function space. And if the function space is well structured, then we can find some basis functions that can approximate the true U. So one example that everybody knows about this structure is the Taylor's expansion. In Taylor's expansion, if f is the true function and the polynomials of x is the basis functions. And what I mean about the little bit of sufficiently abstract setting and the regularization which means like this. So the functions that can be expand as the Taylor expansion in the whole real line is called analytic function, and the corresponding function space is called the analytic space. And in the mathematics, someone who are familiar with the mathematics will know what this means. This is on basis of the L2 space, which is F is a Lebesgue measurable, and finitely the corresponding L2 node is finite. So these functions can approximate, this basis function can approximate any kind of function that is in the function. So in our setting, we are using the Barron's space. And if we assume this kind of structure, then we can always find the basis function. But the natural question arose from this slide is that how we find the basis. And the second thing is the basis of P. And the second thing is how can we approximate U? In 2006, there was a paper published, so-called extreme learning machine, which algorithm looks like this. We randomly sample some collocation points, which is from the Latin hypercube method, and then using the collocation points, we can put that into the true function U, and we get a target function, which is true function. And we can say this is X as an input and the U as target. And then we also randomly sample the WI, the weight, and the BI, the bias, and form a matrix like this. So each load is represented as a basis function, one of the basis function. How so? Is if we take AG as the hyperbolic tangent, and if there is an assumption that sufficiently large n, which is the number of input collocation points is large enough, then we can properly approximate the hyperbolic tangent curve. So each row, we can say each row of the P is representing a basis function. And by using the fact that WI and BI is randomly sampled, so WI and WI is not equal, and BI and BJ is not equal if I and J is different, as surely. So as surely means that we can view this as this. If one wants to, if one put a point in a blank space and through a marker to the board, And then if there's the possibility of these 2 points to be equal is almost impossible. So that is called as-Shirley, which means the possibility of one, the Wi and Wj and Bi and Bj will differ. So by using this fact, we can deduce that all of the low space, so each basis functions are also different from each other. That is, the low space is linearly independent. So by using the basic linear algebra, if n tilde and n is equal, then P is full ranked as surely again. So this problem became a least square problem, which is if there is proper C coefficient of the basis functions, then we can properly approximate the true function U. So to solve this least square problem, we can just use the pseudo inverse, which is explained in the Tuesday by Dr. Hyuk. But the reason why I use the pseudo inverse is that this assumption n tilde is equal to n is kind of absurd because in most cases n tilde is way less than the data points. The number of basis functions are less than number of points. So this is another assumption which is sufficiently large n tilde. So there is a theorem that if the n tilde is sufficiently large, we can properly approximate the C. So we can just use the pseudo inverse to solve the least square problem.
베이시스 펑션의 데이터 개수만큼은 안 쓰겠다.
어.
데이터 개수보다 적게 쓰는 비슷한 겁니다. 근데 충분히 많이 그러니까 고르면 저걸 잘 분석할 수 있다. 그러니까 그래서 디센스 없이 좀 랜덤하게 뽑았을 때 충분히 많이 뽑으면
감사합니다.
안 된다고 스테스케어처럼 이꼴까지 필요 없다.
네.
크기만 하면 된다. 샘플 수가.
Yes, with some rate, it will converges to the true function.
데이터 개수만큼 있으면 래피팅.
Yes, if there is enough data and abundant basis function, which like approximately the same rate same number as the data point, then it will overfit.
Until that means anyway that the number of the basis function of pi. So of course if you have a lot of the basis function, the number of base function equal to the data. Okay, it over, but just two sides of the basis functions. Not true.
That is kind of good intuition because this method is prone to overfitting. Let's move on. Let's see an example because everybody is confused. So assume that we want to approximate this sine function, and we can randomly sample x and wi and bi from the normal distribution and Latin hypercube and form a basis function. It will look like this, and each low corresponds to one tangent, hyperbolic tangent. And since there is a boundary condition, we can just multiply some matrix A, which multiplies the 1 minus xi square to each low so that the left basis function to be look like the right one. And then by solving the least square problem using the pseudo inverse, it will approximate the sine functions like this. So it really very well approximate the function using the basis. But extreme learning machine is not a perfect machine again. As you can see in this example, on sinoid curve, there is no steepness, but in this case, there exists a steepness, and if you zoom in, you can see the wiggleness around the steep, near the center of the steepness, and we call this a Gibbs phenomenon, which occurs from the Fourier transform. And so this Gibbs phenomena is occurred due to randomly sampling the x, the data point, and the wi and wb. So rather than just randomly sample this stuff, we will sampling where it's matter, which is another nearest paper from the same author as the frozen pin, suggests to sample more points near the center of steepness. So we can construct a data-dependent probability measure, which looks like this. So to explain this, we are going to sample a pair of data x1 and x2, which is proportional to this equation, this term, and it is approximated by the gradient of the true function. So around the near of the center of the steepness, we are going to sample a lot of points because the probability of these points can be sampled is proportional to the gradient of the true function u. And after that, we induce a basis functions to have large gradients near the center of steepness by setting the w as also data dependent. Looks like this. S1 is just a constant, and if we put a norm on this term, then it will look like this. Since S is just a constant, and the lower part, denominator, are just a delta x, and we sample a lot of points near the steepness, near the center of the steepness, the delta x must be small. So actually this LW, the weight became large. So it will look like this with basis function sample from the swing method. As you can see, if you zoom in, there's no Gibbs phenomena in this case.
Sorry. Could you explain why this phenomena occur due to the constant number?
Oh, sorry.
So
Because there is a term called homologous endwidth, which explains if you want to approximate a continuous function with finitely many functions, basis functions, but if the explanation power of the basis function, for example, like the number of the basis function is not enough, then it struggles when the gradient is steep.
related to dependence or related to the that enough number of something?
Both, because as you can see on the well, if we sample the weight and bias independently, like uniformly, as you can see on the endpoint, it is very complex, right? But as you can see on the swing method, due to the fact that their gradients are concentrated in the center of the steepness, as you can see at the end, it is quite not very complex. Its gradients are very flat.
딱 하더라고. 그레디언트가 되게 보면 습한 곳에서는
뭐 많이
많이
봐야
봐야
되는데.
되는데 전역고 넓게 해서 같은 비율을 뽑으면 그만큼 훨씬 더 많은 게 필요하죠. 근데 이거는 이쪽에 좀 약간 자원을 몰아줘가지고 적은 걸로도 좀 효율적으로 다
진행해볼까? 한번 보자. 한번 해볼게. 지금 한번 해보자. 일단 so everyone we should think let's think in this way. Here is a sine function. That's what we want to approximate. And what is the typical way to the neural network to approximate the function? We put the data of this black line to the neural network, and then using the gradient descent, we estimate all the W weight of the neural network. Then we'll get this black. That's a typical way. But his point is we want to approximate function without doing the gradient descent. Right? How to do is anyway, here is a tangent hyperbolic is function is a basis. But the basis it's a tangent hyperbolic function is basis. And W1 and B1 is the parameter of this basis. So depending on your choice of W1, B1, the shape of the functions are changing. So this is a basis 1. You can think that this is x-axis, y-axis, z-axis. Does it make sense? So we have x-axis function, y-axis function, and g-axis function. For instance, here, let's assume that we have just this 3 function. Okay. So then, what is the coordinate? X-axis is 1, 2, 3, 4. We have coordinate. Right? So, if coordinate is 1, 0, 0, then what means 1 times x coordinate function and 0 times y coordinate function, 0 times z coordinate function. If our coordinate is 1, 1, 0, that means we will sum the x function, y function, but we ignore the z function. In that way, we can generate the main function. And then, but the problem is that what kind of coordinate will make this sine function? How to identify is a linear regression problem. So let's ignore this A. So if this is inverse, right? Inverse means if we move it here, pi x is basis, right? The C is our x, y, z coordinate. So pi function, x function, y function, z function, coordinate equal to, we want to make that graph. So that it's a really linear algebra problem. So that, and according to the previous theory, we have a sort of the enough sampling and enough number of the bases, then we can express this sine function with this. You can see that this black is original function, and then I think what he drove is this purple is summation or what?
The black one is the summation.
Oh, black is summation. Okay,
But
so
yes,
okay, I see. This purple, red, blue are basis times its coefficient. Does it make sense? So this is x coordinate, y coordinate, z coordinate. If we sum it, then we will get this black curve. You can see that compared to top and bottom, similar or not? Very, very similar, right? So that this is very good. We did only ax equals to the b. And here we don't have a gradient descent because this is vector, right? Vector times inverse of the matrix. Is there any gradient descent? No. we can serve it in the MATLAB. In the MATLAB, we can do the AX equal to the B, and then inverse of A, we can serve it, right? So it's very, very good. We go next. The problem is here. But if our function is not the sine function, if we have this crazy jumping time function, unfortunately, this approach require many bases, because to express this steep jump using this sort of the smooth function, we need sort of the crazy long summation, so that sort of it's not current typical state seems not working for these cases. So, but the author suggests a very smart way. Yes, yeah, here. Yeah, good. So when we have this kind of, let's say, when we have this one basis, we can sample the point equally. That's one way. Or for this purple curve, let's just focus on this purple curve. We want to use this purple curve to approximate this black curve. Where do we need more point? Maybe we want to spend more energy here, right? So that how they choose the sampling point for the axis. Here is to sample point distance, and the top is we plug in that value, I guess, to this original function. That means it's just so slope of this function. So if we have a high slope points, then we sample it. And then another important thing this point means is this is a weight for which base function we will use, and then we will give a high weight for which have like a steep change in this black point curve. So rather than smoothly change here, if we have a more steep change, we want to more frequently choose that base function, if I understand this correctly. But anyway, the point is, key is this, he wants to change the gradient descent optimization problem to the linear algebra problem. But bad thing is we have to carefully choose the basis function. And here is some strategy to carefully choose the basis function. Okay. And then maybe we can go back to that equation, original general equation. And then why this approach working is, according to this theorem, as long as we have a large column means we sample the many point of, for instance here, we have many orange point or not. Correct? Because we have large enough of this orange point, we can approximate this original basis function. For instance, we sampled only 3. And do you think with these 3 points, we can represent this basis function or not? No, right? So we need large enough number to approximate this function. That's one condition. We need a large enough sample, sampling for the basis. And another condition is we also need large enough choice of the different type of the basis. So X, Y, Z, and then some dimension. Then it's sort of the guarantee that we can do this. But the problem is always this kind of theorem is 10 or 20, 30. They're large enough, but is enough? Yes. That means try and out. Adjust this, it worked, done. If not, keep increasing. That's the strategy. So, Seunghun, I know you're the first presentation. So one important lesson is when you want to introduce this theory, always better to show the example first.
Sure.
Because this is a more, so actually it's the same for everyone to you. So think about it, seeing this and then next slide, is it better, or next slide first and seeing this theorem is better for you? Just think about which is easier for you to understand. The example first and then theory, or theory and then example. Example is counter flow, right? So when you teach the mathematics, write down the theorem, theory proof, and then here is the example. I know this is typical of math faculty to do, but unfortunately that only work for the very smart person. I know math faculty is very, very smart, so they are okay about the approach, but in this world, 99.999% are not that smart in terms of math. In particular, our audience could be biologists. That means, rather than put all this theorem first, we should show the concrete example first, and then going back to this theorem. Make sense? 그래서 승우이도 example 먼저 학교 가서 발표할 때 example 먼저 하고 그 다음 너의 메인 디오렘을 보여주는 게 사람들이 이해하는 것이.
네.
됐나?
Yeah, thanks for the additional explanation from the professor. And let's move on. So the part one of the presentation is over, and we're going to move on to the part two. So now we assume on the partial differential equation to looks like this, and the boundary condition would look like this. And the initial condition will look like this, which is the same as the well before explained the Burger's equation. And the start of the problem is the same. We solve the basis function for the initial condition, which is u, x, and z 0. So it's just the same. We already done this. So for the basis function, we use swing method to sample the basis functions, and we solve the boundary condition term. And after that, we approximate the initial condition function, which is already solved, the sine function, with the least square problem. And this makes the initial condition loss to be less than epsilon, which means that sufficiently low and accurately approximate the function. And for technical reason, due to the fact that if there is a numerous number of basis function, it will be prone to overfitting, and the computational complexity would blow up. So we just apply the S3D singular value decomposition on the basis function space. So it will look like this. The left-hand side is our original basis function, and right-hand side is the singular value question. So this is the V and our singular values. The singular values for the data point. So we just use V to multiply into these basis functions to mitigate these problems. And after that, we're going to derive the answers. But before that, as professor said, I will just show the example first. So the basic idea is to assume that these our generated basis functions are the span of the Barron space, which he assumes that UT are in those function space, so that we can approximate those functions using our well-known basis functions. So
모든 시간에
Well, that's a strong assumption.
yes, it is strong assumption, but as you can see the example, it works. So in this problem, we are using ELM method. As you can see, and as well explained, those on the bottom side, those swollen hypertangent curves are the basis functions, and those amplitudes are the time-dependent coefficients. So it varies as the time goes.
이니셜 컨디션을 잘 어프로시메이션 하는 베이시스로 나머지 t 시간들 다 근사를 나.
근데 약간 그런 very inadequate to me is what he say is let's decide a basis function from the initial condition. Our initial condition change was sine curve. To approximate sine curve, you may need just one or two bases.
Yes.
To be frankly.
But-
And then as time goes, that two might not be enough.
Yes, so that's the reason why we choose a many basis function at the start, but it start to approximate the initial condition. The singular value of they just reduce the number of the basis function. It can be decided by the hyperparameter, but by lowering the hyperparameter, we can use a lot of basis functions.
이니셜만 다 맞추는 이니셜 컨디션만 다 맞추는 걸 주는 게 아니라 사실은 이 이니셜 스페이스를 충분히 다 근사할 만큼 베이시스를 충분히 많이 뽑아야 돼요. 그러니까
하나의 이니셜 컨디션이 아니라 수많은 이니셜 컨디션을 다 테스트해야 돼.
No, it's just one initial condition.
근데 그래서 랜덤하게 뽑아야 돼요. 하나로 그러니까 그게 이니셜 컨디션을 잘 수렴한다고 해서 나머지 t까지 다 수렴한다는 보장은 없어요.
Yes, that's the assumption number one. Number three.
그래서 이걸 그 가정을 하고 충분히 그 나머지 시간
그 충분히 많이 뭘로 도움이
그걸 모르죠 사실.
뭘로 그럴까요? 이니셜 컨디션으로는
Actually, those kind of mathematical backgrounds are in the sampling various matters paper, but it only assumes the initial condition value. But if we experience,
랜덤하게 뽑고 근데 거기에 하나의 조건을 붙이는데 그래도 이니셜 컨디션은 하기 이 정도 느낌인데 이니셜 컨디션 하는 일이 그닥 있나?
이후에 그러면 시간에 따라서 개수들까지 걔를 어떻게 구할지가
이제 그 개수의 초기 값은 주어지는
그렇죠.
그게 핵심인 것 같아요.
맞아요.
베이시스를 선택하는 게 아니라 코에피션트를 선택하는 게 핵심.
yes, the coefficient is the one that is time dependent.
Then we should then explain this way. Basis function is not determined by the initial function.
No, the basis functions are dependent on the initial condition.
Dependent?
Only depend on the initial condition.
그 이니셜 약간 이런 거죠. 이니셜 컨디션을 잘 맞추는 게 필요 조건.
Only dependent라는 건 이상한 거. 이 컨디션 하는 역할이 그렇게 없을 것 같아요. 컨디션만.
교수님이 걱정하시는 상황은 이니셜 컨디션이 너무 쉬워서
너무 쉬워서.
너무 작게만 잡아도 충분히 근사가 잘 됩니다. 걱정하시는.
만약 only dependent은 이니셜 컨디션
그렇죠.
사인 펑션 하나로 끝날 수도 있는.
그건 해보고 안 되면 다시 처음으로 돌아가는 사이한 일을 할 수밖에 없어요.
그렇지. 약간 only dependent란 스테이트먼트가 굉장히 이상한. So I think a better statement might be we select a large number of bases, which is quite general, but to check. But the first test is at least it should successfully approximate the initial condition. That's just necessary condition, but not sufficient condition. One, and then number two, so we don't know the coefficient of the and then from that initial condition we can determine the coefficient of the basis. And then there could be just initial condition on the basis to how they evolve to. Yeah, so that's why basis function is only depending on initial condition. Here it's like a necessary and sufficient condition. So that's to me too much statement. 일단 네.
So, as we see in the example, let's move on to the assumption number three. So, yes, as before mentioned, we assume that u and ut or any other derivatives with respect to t are in the Barron space, which is spanned by the basis functions, which is sampled from the initial condition. So now we can approximate this function true u by u hat, which looks like this. So basis function and the coefficient. So this means that we are going to approximate this kind of function, but while using the same basis function that is sampled from the initial condition, but only the coefficient. Their evolution is the key method to approximate the dynamical system. So next step is to plug in the approximation u and ut, u hat and u hat t into our original PDE on the top, and it will look like this. And after this, we can just use the pseudo inverse again to solve the answers, which will look like this. So on the first equation, we just multiply the pseudo inverse to both sides. And it's just an ODE system, which is independent of space X. So next step is just to solve the initial value problem using scipher. Then after this, I will explain some example, which is Bezier-Burger's equation, as I always use. The PDE equation looks like this, and boundary condition and initial condition looks like this. To approximate the Burger's equation, we use u hat as usual, ut as same, but the derivative with respect to x is a little bit different. The derivative goes into the basis functions. So this basis functions derivative with respect to x is composed of the Hadamard product, so that the weights are kind of pops out as a coefficient. And also for the second derivative of x, it looks like this. So while using this basis function, we already solved the boundary condition and initial condition. So we can ignore it. And only term we are going to solve is the PDE, which looks like this when we plug in all the equations of the approximation into the original Bezier-Burger's equation. Plugging this approximation into the original system, then it will look like the one below. And as always, we can use the pseudo inverse to calculate the CT, C sub t and t, which, as I've shown before, the time evolution of the function will look like this. On the ELN also, it shows the Gibbs phenomenon as well, but in the swing method, this does not show, because there is sufficiently many basis function that has steep gradients on the center of the steepness. So as a summary, we sampled the basis function and solved the boundary condition and approximate the initial condition of the function and solve the coefficient as the time evolves. Then it will solve the PDE system like an ODE system without need of gradient descent.
That means actually, first, did neural network or not?
It forms like network, but without gradients.
It is not, I mean, it's kind of like neural network because ELM method and swing method has a layer. It's a single layer perceptron, but it doesn't use the gradient distance.
Well, single layer perceptrons basically solving
linear system.
Yes.
So it's a single layer. So
Yeah, that's right.
oh yeah.
So we have
Oh,
X-ray
yeah,
function times coefficients.
So
Yeah.
but can I say it's a linear algebra problem?
Linear algebra with choice of non-linear
Linear
basis
basis.
function given by the equation function.
So it's a very different from the typical pin we imagine. Typical pin we have many layers.
Many layers and many processes.
Not like neural network.
Yes, it is not a neural network.
그러니까 기존에는 예를 들어서 이거를 에뮬레이터로 하는 거, 세타를 몇 개 정하고 여기서 그냥 OD를 풀어서 그냥 뭐다 들어오면 짝하는 느낌. 네, 네, 이건 PD랑 좀 다르긴 하겠다.
PD에서 프레셔 배력을
그래 맞아요.
그렇게
그 separation of variable, separation이 조금 다른 게 separation of variable 해가 그냥 x dependent, t dependent.
아니, 나눠서
나눠진다는 게 사실 separation 솔루션인데.
할때 진짜 맞더라고. 아디파이 X는
그렇지.
원시 프레셔 해버리고.
It is same concept, but yes, it is kind of absolutely different.
그 separation of variable solution 같은 건가? 맞나? 우리 원래 PD 할때 원래 x는 u, t면 xu 곱하기 xt 두 개에서 집어넣고 포프에 갈라지게 뭐
제 생각에는 그러면 베이시스 하나를 가정하는 상황.
그 지금 베이스 하나지.
베이시스에 사인 원 쓰고 이런 거.
근데 베이시스가 똑같은 시간에 대해서 같은 개수로 우리
여기는 그럼
저 CT가 애초에
이거가 두 개의 차이죠.
영역별로 다르게
그렇죠. 그러니까 베이시스가 자기들끼리 알아서
음.
왔다 갔다 해서 얘를 맞추는 거랑 하나의 베이시스가 똑같은 개수로 하나로 쭉 밀고
그
나가는
차이가 있어요. 그러니까 어떻게 보면 우리는 x of u 곱하기 x of t 집어넣어요. x1 u 곱하기 x1 t 더하기 x2 u 곱하기 x2 주 여러 개가 있다고 생각해요.
약간 저 사이 베이시스로 전체 도메인이 이렇게 그렇죠. 여러 공간으로 나뉘 있는데 공간에 솔루션을 프로젝션을 한 다음에 솔루션 결국 타임스 세퍼레이트를 들려줘서
영어 공간들과
맞지.
But anyway, the summary of this talk is we don't need a fancy GPU to
Yes, it only use CPU. Yes.
it's just linear algebra. And now actually it's
Is the part boundary compliant and this paper or is one of the biggest work boundary compliant
Boundary compliant is on this work. On this paper is on the appendix.
so they developed the party.
I don't think they developed, but it mentioned.
너의 연구에 좀 성장성.
네.
어떤 거는 좀 TV가 항상 우리가 저기 항상 깔끔한 걸로 유도가 된다는 근데 TV는 그러니까 제가 이분이 아예 없어. 한 공간에 그냥 공간에 이분이 아예 없는 깔끔한 거 지금 거기서 오고 있으면 사실 컴퓨터 영역에서 그냥 한 번에 그 이뮬레이터가 생겨버리는 좋은 우리 PD로 거기서 쓰는 거 보지가 있어. 그렇죠? 저는 그렇게 생각해요. 조금만 수학적으로도 항상 약간 이런 방식으로 n이 충분히 클 때 그 모든 걸 다 그렇게 할 수 있다는 것도 볼 수 있어.
I can't find the appendix in the appendix, but they mentioned that they use the boundary condition compliance of the previous works. So you can just apply the metrics, that hard-coded metrics, to the basis function, or you can plug it into the ODE system as the auxiliary ODEs, but it is very complex, so I didn't include in this slide.
In this case, they could be using all minus x or
Yes, just hard-coded metrics.
that's just a
Yes, if you know if you have a full prior knowledge of the PDE system, then you know the boundary condition, then you can apply this kind of method if it's possible. And if it's not possible, you can just plug it into the ODE system. Then it can automatically solve as the time evolves. Yes.
You mentioned that the swim method is basically to fit the basis function to a steep region. But in the case of the vicious variable problem, I believe the sine function shifts and the steepness region kind of remains. But what if in a case that a steep region shifts, like this shift steepen somewhere else, and now the centric basis function doesn't work in that region, but it now should fit to some other region?
Yes, that is very excellent question, and it is kind of impossible because the translation of to the y-axis is possible because there is a there is a one term. So coefficient can move in the y-axis, but moving throughout the x-axis, shifting of the x-axis is properly approximating those kind of dynamics is impossible. So all those suggest to divide the time stem. So if your time has a 1 to t, then divide it into the numerous time windows, then make the basis function for each time window, then just plug it in all together to approximate the system. Any other questions?
I know today is challenging, right?